Hello there, welcome to a problem session. So this is a numerical problem on the energy and momentum flow in electromagnetic waves. I assume that you have seen these things, except that if this thing is going along the z-axis, then it's just a kz. So if k is the it's called wave number vector, and if k is going along the x-axis or z-axis, so you have like a k z hat. So this will be if towards positive z-axis, if wave is towards z-axis. If it's towards negative z-axis, it's going to be minus k z hat, assuming this is positive. If towards negative z-axis. So when you write in a vector form like this, you can capture any arbitrary direction the wave is going. Okay, so you know this, and for electromagnetic waves, the electric field and magnetic field direction in space is given by these guys, and of course the sign of, if this is positive or negative from working out this. But they're completely in sync. They're completely in sync, and these guys are perpendicular, and so are these guys. And these are the amplitudes. This is called amplitude. The plane in which these two vectors lie is perpendicular to the direction in which the wave is flowing, and the magnitude of these amplitudes are related like this, and this wave number, magnitude wave number, and angular velocity is related to the speed of light. So I hope you know this. You watch a video before this video if you are rusty on this, or look up in a textbook. Okay, so another thing that you might know already is energy density in the electric and magnetic fields. So in E and B fields, so the electric and magnetic fields, regardless of if there's anything else or not there, they have some energy. And energy is given as energy per unit volume. So the formula for that is that, and you can write in a dot product if you write E dot E, and this epsilon naught. And same magnetic field, energy in the magnetic field. So for instance, you have a coil and you pass a current, and so in this space here you have a magnetic field, and that space is empty, but it has energy because it's magnetic field. So that's what this is saying. And this was also same, like if you had a positive plate, a negative plate, and this is empty, but this area is empty, but doesn't mean it doesn't have energy. It has energy density given by electric field. Okay. Similarly, momentum density is given by this expression. Momentum will have a vector, so this is a vector, and it is this much momentum per unit volume, and E cross B tells you, when right-hand rule, is the direction in which the momentum density is pointed. The intensity, which is a very common phrase that you use, the intensity of light, which is the problem here. In this problem you have intensity. This thing is actually intensity with this word average. So what it means, I put an angle bracket here for this formula, which says intensity is a time average of this quantity, and absolutely I put this as saying that this is going to be a vector. It's a magnitude of that vector. So this is a positive quantity, and this may be negative, this may be, but this is a positive quantity, and we can we have to do time average. So sometimes people write a little letter t there to indicate you're doing averaging over time. Now, because it has momentum, so if you were to say the waves are flowing this direction, and you put a barrier there which absorbs it, there will be, because of momentum, they'll come and hit the next, you have a force on it. And so force per unit area of cross section, force per unit area of cross section is the pressure, right? So there will be radiation pressure. So you have a momentum density. Radiation pressure is not radiation pressure density, it's just radiation pressure on that. So although this looks all very similar formulas and very easy to get confused, by the way, and because the formula are also similar, very easy to confuse, sometimes it's helpful to write in terms of what is called Poynting vector. So just use one formula and use C equals to 1 over square root of mu naught epsilon naught to write all the other formula in terms of the S. That's a very common practice. I'm not going to do more on that, but just so we need to find this 4 waves like that. So here is a question. Question is on the so here is Earth, and here's atmosphere, and Sun is very far away. So these are kind of plane waves. You can think of this as plane waves. So these are plane waves coming in. So over here, if I look at a unit area, in that area, the energy is 13. It's not sitting there. It's actually energy is flowing through that area at the rate of 1360 joules per second. So sometimes people like to think it a little differently. This thing here is power. So that's the power, and you have power per square meter, meter cross section. So sometimes this entire thing is called power flux, So there's another way to say it. It's just another word or phrase, but people commonly use it. So find the amplitude of electric and magnetic. So what we're supposed to find here are not electric and magnetic fields, because they're in the wave. They're going to be like this. This is the thing we're supposed to find. This and this. Okay. So what is given is the average, a time average. So all of this information will be averaged out, from these waves. Okay. So we need to start from here and put it in there, get a time average, and so we'll have a formula in which we can plug things in, and we can get the answer for that. That's how we're going to get. Or if you have a formula of intensity, so what we want is a intensity equals to something. It's going to be an electric field and a magnetic field. It's going to be E0, B0. So it's going to be something E0 square over C, but using B0 equals to E0 over C, or something C times B0 square. So because this is given, if we know what that is, sometimes you can just memorize this formula, so you don't have to derive it. But this is the fundamental formula, and from there we can once you derive it, you just memorize it to save time in the test time. Okay. So using this, will be very easy in this particular problem to find out what E0 will be, what B0 will be. That will be the strategy. And then if we know what E0, B0 is, we to get average energy density, we need to find a formula this is average energy in electric, is energy in electric field, energy in the magnetic field. We need to add them up and find their time average. Okay, and because we would have known this, we can actually get the time average quite easily. Okay, so with that, let's let me pause this and then give you time to work on it yourself, and come back and try to do this problem. Okay, so this was given, and there was a strategy. So for electric field and magnetic field, we get this. So this quantity is going to be 1 over mu naught, and E cross B is just going to be, they're 90 degrees to each other, so it's going to be just, it's going to be E0 sine this thing, B0 sine the same thing. That's it. And we're going to do time average, and so this one, so you can see E0 B0 is going to come out. It's going to be 1 over mu naught E0 B0, and time average of sine square. Let's see k equals to k z hat. So we can pick one, kz minus omega t. So what's the time average? Time average is 0 to a period of time. A period of time will be, say, just the wave. Actually, this function, period of time, just for sine, period of time is 2 pi over omega, and period of this will be half as much. So t2 is going to be pi over omega. So we just have to 1 over t2, and that's going to be 1 period, because when you square it, it's going to repeat at half the period, right? Okay, so if you didn't understand why the period will come half, you just work it out. It says sine theta has a period 2 pi, but sine square theta has a period only pi. Okay, so this is going to be sine square kz minus omega t dt. So you have to do this integral, and you can show that this is actually equal to half. Okay, now it's kind of very easy to show it by half, by just say this is 2 times 2. So cosine 2 theta equals to 1 minus 2 sine square theta. I mean, it has other expressions, but so this thing becomes 1 minus cosine 2 theta, so 1 over 2t2, 0 to t2, 1 minus cosine 2 of this dt, kz minus omega t. And so this one just gives me 1 over 2t times, and this next one just gives you 0, because cosine over a whole period is going to give you 0. So this is half. So this whole thing, going back to here, this whole thing will be half. So it just turns out to be equals to 1 over 2 mu naught E0 B0. Now E0 B0, I will just say B0 is going to be equal to this over C. So this is, as earlier explained, 2 mu 0 E0 over C. So I want to get electric field magnitude. That's one of the answers. So this whole thing is equal to I. That's the I that's given. So so E0 is going to be 2 mu 0 Ci. This is going to be positive, because that's by definition a positive quantity. and mu naught equals to 4 pi times 10 minus 7 SI units. It's 10 SI units. So this is square root of 2 times 4 pi times 10 minus 7, 3 times 10 to the power 8 meter per second. Intensity is 1340. All SI units. This is an SI, this is an SI, this is an SI. So energy, this whole thing will, the unit of this whole thing will be a joule, SI unit. And let's work, this is positive 8. Let's work this out, and I'm gonna give you an answer. Okay, so I just noticed something. This will be Newton over Coulomb, Newton over Coulomb, Newton over Coulomb, right? This is not energy, it's electric field. Electric field. And one way to remember the unit of electric field will be F equals to F on, say, charge Q is Q times the electric field there. So if this is Newton and this is Coulomb, then this would be Newton over Coulomb. So that's my mistake. Although you can work out the energy units and can be quite complicated, right? So you have to unit of mu naught and C and then I, and then you can work out some other way. But you will end up with some, instead of Coulomb, you might get a amp. So like because you're going from the unit of magnetism, usually in amp. So to do that, you have a Coulomb per second will be amp. So Newton per second. So it will be like that. So this will be amp. And sometimes you have a Newton over meter, that will be joule. So you have a meter times second. So this will be joule, and this will be watt over amp times meter. So it's like several units you can use here, but the standard unit for electric field will be Newton over Coulomb. Okay, so that's the electric field. How do I get magnetic field? Do I have to go out and work all the thing all over again? Not, right? Because electric field is in this electromagnetic waves is equal to C sine B naught. So the B naught is going to be simply E naught over C. So just divide by C. 2338.5 over 3 times 10 to the power 8. And the unit of this, because it's going to be Tesla or just a T. Okay, so now we got electric field, magnetic field, and we want to know what's the energy, average energy density will be. Okay, so that's the one I'm going to work out next. So do I have to start out from here? And so one know average energy density. How do I get it? So one way to do is start from here, plug those things in there. So we want energy E plus energy in the B. So total energy will be like this. So we want average energy density. So that will be an average energy UE plus average energy UB. And then I'll have to say, okay, this will be half epsilon naught E dot E. I have to time average this guy, and 1 over 2 mu naught B dot B. Okay, that's you can go through the process. You can see this is going to be 1 over epsilon naught, and just like that is going to be half E naught square, because time average will give me half, and the other one will be similarly 1 over 2 mu naught is going to be half B0 square. And because E0 B0 is similar and mu naught C is equal to this stuff. We can write this together, and you can show that this is half epsilon naught E0 square, because this will turn out to be equal to that. And so two of these added up becomes like that. Now, if we know that this is average is going to be like this, you can see the intensity formula was like that too. So I can actually try to write intensity in that form. So this should be equal to, I want to get half epsilon naught, so I will have 1 over epsilon naught mu naught c times half epsilon naught E naught square. So I can write this in that way. So this is just going to be, you have a c, and c is equal to square root of mu naught epsilon naught. So it's going to be square root of epsilon naught mu naught. This cancels out like that, and this is the average energy we want. So you can see the average energy is related to intensity by the formula C here. So this is equal to C times UT. So working this out actually tells us that we don't need, once I have intensity, I can get energy density very readily, and I don't have to plug in and do lots of the work. So using this UT that we want, and I can take intensity and divide by C, and intensity was 1360 watts over meter square, and C is 3 times 10 to the power 8 meter per second. So you can see that this will come joule per second. So this per second cancels per second. 1 of the meter, this is going to be combined with meter cube. So this is going to be 13.6 over 3 times 10 to the minus 7 joules per meter cube. So that's the energy density. So in a 1 cubic meter, you have this much energy. So let me just complete this. And so if I take 10, so this is 4.53 microjoules per meter cube. Okay, so that's how much energy is out there in like an empty space, just above the Earth's atmosphere. So this completes the calculation for this problem. But you may wonder, how about these other guys, momentum density and things like that, and radiation pressure, and you may want to calculate them out. Don't try to do more work than necessary. So once you do these out, try to do time average of these guys, and it's the same trick. You can write everything in terms of the same thing, and let's see if how that would go. Okay, let's look at the momentum. Okay, so we're going to say it's going to go into the z direction, and E and B are E cross into B, so B, this is 90 degrees, is in the XY plane. Okay, doesn't have to be X and Y direction. Maybe this is the X direction and this is the Y direction, and this is an XY plane, electromagnetic field vectors. Okay, so when I look at the momentum density for this case, so we've taken, maybe you can do it like E, this thing is E0 I had x direction, and B0 is gonna be B0 j hat, and so K is K z hat. So we'll choose that just for, so we have a momentum is epsilon naught E0 cross B0, and then sign is the same, so sign is square kz minus omega t, and we could choose phi e equals to phi b equal to 0, phase constant. And so this is going to be a momentum density, let's call it little p. Okay, and we want the time average. So we want the time average. We already noticed that this is 90 degrees going to be, so epsilon naught E0 B0, and the direction is z hat, in the z hat direction. This is a unit vector. Okay, and so what we get E0 B0 times half. Time average over that adds half. So you have a z hat. We want, let's see, momentum. I want to have magnitude, so we don't care about the direction. So you have half epsilon naught E0 B0. Now you can see that intensity of 1/2 mu naught. So you have epsilon naught half 2 mu naught and E naught B naught. So I put mu naught down below, so I put mu naught up above. So this whole thing, becomes intensity. So you have a mu naught epsilon naught intensity, and so mu naught epsilon naught is 1/c square intensity. Very cool, right? So just knowing intensity, I'm get the momentum density, and the direction we just go E cross B, whichever the electric field is, magnetic field. A direction will be direction in which the wave is traveling. So you don't have to do cross product. You say, okay, the light wave or the electromagnetic wave is going in that direction, so momentum is in that direction for us. So this momentum distance, so it's pretty, just from intensity I get it. With this factor gonna go different with different things because the way definitions are. The radiation pressure, well, it will come from, so wave is traveling is that way, and I say I take a 1 unit of area, and so how much this volume, how much of this momentum is coming on this, right? So the force, so I want to get the force per unit. This, so if this was the area A, so don't have to area A. So waves are coming in, so this will be how much momentum has come in, how much total momentum, not density, but total momentum have come in how much time t and A. So in delta t, C delta t, so everything that's in this volume would have come in here. So A delta t, so I have this much momentum. Let's just do force. I had this much momentum, so I'm going to just call it like that. That much momentum in this whole volume. That volume is A times C times delta t. So this is the momentum density, and this, and so I can see the area cancelled out and delta t cancelled out. So P times C. So this is the pressure, radiation pressure. So already we can tell. So radiation pressure on average. So this on average radiation pressure average That's C times the pressure density, and pressure density is intensity over C square. So intensity over C square. So that just reciprocally intensity over C. Pretty cool. So just from intensity you can get all the other stuff. But the fundamental formulas you got to remember. Otherwise you got to remember the cases and you'll remember all these other formulas. I tend to remember the fundamental ones and kind of work out every time these other formulas, or have to look it up if I'm in a hurry. But if you're preparing for some tests and you expect these kinds of things to be on the test, I would recommend kind of, remembering some of the basic formulas and how to go from one to the other. The most basic one to remember is just this. And then you can see how that other things relate to it. Hope this helps. If this helps, you can hit the like button so that other people can get to it easily. You can subscribe to this channel if you want to get more of these kinds of reminder for these videos. Or you can check out my website. There's a much more discussion of many other problems on this. Okay, take care. Bye.